So the recording is on, just for
Got it.
everyone to just to know it.
So I've heard five, I've heard six. Anybody else? Anything else?
A 6. This final answer.
So I see six. So nothing there. There's one right there in the second row.
Maybe 7.
Oh, there's two. There's three. Nothing there. There's four. There's five. There's six. There's seven. And that's all. I'm assuming nobody else sees more than seven. Am I correct? All right. Look, that just takes us back to what we were doing yesterday, and that is simply counting. Mathematically, all we did yesterday really was talk about counting and how, when you're in an unfamiliar situation, how easy it is to make mistakes. Someone joined us yesterday after you people were gone who teaches mathematics, calculus. And I said to her, one of the biggest mistakes I see when I teach calculus is people just not able to count correctly, not able to do simple arithmetic correctly. They make mistakes in an unfamiliar situation. And the same true, that's the point of the locks here. Not familiar, not easy to count, but all you have to do is actually count. And trying to get it right doesn't just happen. It takes a little extra work for that to occur. All right? Gonna make this a little larger. We made the point yesterday that our mathematical system is set up with only 10 digits, 10 different characters, 1 through 9 and 0. All right. And that makes it look very simple to work with. But now things start to become a little bit more involved. All right. It's not just what digit we use, it's where we place them that matters. It's our number system, and your number system has something called place value. That one that we see in 1, 2, 3, 4 decimal point 5, that one that we see isn't just a one. It's a 1 times 10 to the third, or 1,000. 2 times 10 to the second, or 200. 3, 4, and 5 times 10 to the negative first. Does that place value, does that expansion, is that familiar to all of you? Yes? No? Do you understand? Do you understand? Let me click on Dora. Does that look, have you seen that expansion before?
Yes.
Yes. Okay. So it's not new.
Yeah.
And the bottom line is it's not totally universal, but it is pretty common throughout most of the world that we all can read numbers that are very much the same. We don't get trapped by differences in language. So yeah, our system isn't just about 10 digits. It's about also something called place value. The problems we come across when it comes to counting are accuracy. And the other problem we come across is numerals for any one number. In this country and in your country, the number 7, you see the shape there, all right? But that also could be written as VII, right? What is that? What's that VII?
Rome system.
Yeah, it's a Roman numeral system, right?
Yes.
Which in older time and with older times was used, but and times well before us, right? 2,000, 3,000 years ago. But today it still shows up as far as it just show you how powerful it was, how powerful the Romans were. It shows up on buildings and so forth as dates for the most part. So yes, 7 in Roman numerals. 7 when it comes to tallies. Just 1, 2, 3, 4, 5, 6, 7. All right. That what looks like a T is a hieroglyphic to represent the number 7. And the symbol that you see after that is Chinese to represent the number 7. So it's not just the numbers, all right? It's the numerical way of representing it that can change, that makes things a little more difficult. Then we've got large and small numbers. We've got a very large number there. The US national debt, I don't think that's up to date. I think it's more than that these days, all right? But that's how much money the United States owes other parties, other countries, mostly China. Can someone read that number for me? Let's pick on Max. Can you read that number?
Yeah, I can read, but now I spread this number on 1000 million. 31 billion, yes, billion and 454 million 525 тысяч 100,000, yes.
Okay, let me hold you up there because you're right. Look, it's such a large number, it's difficult to really comprehend how much that is. And it's also difficult to come up with, you know, a way of just reading it accurately. This brings 2 points that may be different in your life and your system than here in the United States. Max, do you use commas between each of those periods? And that's what you call the 3 digits, a period. Do you use commas or do you use a decimal point?
No, I'm not use no decimal point, no comma while I write or read this. I'm use this like I don't know. I'm translate this word, this 3 number to language and add to this word range, like 1,000, millions.
But do you actually add a word? You know what I mean when I say a comma, right?
Yes, yes.
Yes, got you. Do you, when you write this number, use a comma or do you use a point? Neither?
No, in if we have I don't know, like not part of number, I'm not use a comma or decimal point. I'm write without this.
You write without this.
Yes, because if I write the decimal point, it's mean this the next number is the part of another number.
So if you wrote this, would you write 3, 1, 4, 5?
5, 4, 5. Yes.
I'm sorry. Let's get that correct. All right. So 5, 3, 1, 4, 5, 4, 5, 2, 5,
5, 2, 5,
4, 0, 3,
3, 8, 5, 4.
8, 5, 4. And you would not put anything in between?
No.
Nothing.
No, sir.
Just its whole number. We use comma and dots when we use fractions. But if it's whole number, we write without commas, dots,
Nothing.
or etc.
Isn't
We
that
can use a gap.
like between numbers.
Say it again.
We can use a gap between numbers, like
A gap. Okay,
Yes.
that's what I'm getting at. So you might do something like, well, it's going to, because of the lines and spacing, but as I fix it, 454.
yes, like this, exactly.
You
Yes,
would do something like that,
yes.
right? But no punctuation, no comma, no period, nothing.
No, no.
Interesting. Okay. See, again, just culturally, that's different because we can't write that number without a comma. All right. It just makes it clear that there's that separation there and that it can't be missed. All right. And so let's get back to the original point here. The original point is that's a difficult number to just read. All right. That 31, by the way, and here comes another cultural difference, perhaps. That 31, the 3-1, isn't billions, as Max suggested. If it's not billions, if it's bigger, what is it?
Trillions.
Trillion, right? 31 trillion, 454 billion, 525 million, 403,854, right? Max, do you think you could read that for me again?
31 trillion 454 billion 525 million like 403 thousand and 844.
54.
54.
Right? So great, perfect. Sometimes people will read perfect. Sometimes people will read that number and they'll use the word and. So they might say 31 million or billion, I'm sorry, 31 trillion and 454 billion. There should be no and in there whatsoever. The and shouldn't occur unless we get down to decimals. And so, yes, when you read it as just the separate period and with whatever its period name happens to be, whether it's trillion, billion, million, thousand, or just units. Okay, great. There's a better way to represent that when it gets that big. Do you know what scientific notation is? Is this new or old or what? Oksana, do you know what scientific notation is?
Sorry, no.
No. Okay. So you've never done anything like this. I'm going to do 3 decimal point. Maybe I'll do a 1, 4, 5, 4. I'll just go that far. And then I'm going to do times 10 to the 3, 6, 9, 12, 10 to the 13th. So I've got to raise that to a power. So I'm going to do 13. Is it going to do it? Oh, right down there. There we go. 13.
I apologize. It should be 5, maybe. If your approximation, its approximation should be 5 at the end. No?
No.
Why no? It's 5. It's like you approximate. It's the next is 5.
Oh,
So it
well,
should be,
you're talking about right here.
yeah.
I'll come back to that part in a minute. All right.
Okay.
The first question, however, is this recognizable? Have you seen any of this? Oksana, have you ever seen that before?
Approximation we use in information technologies, for example. and we use just letter E. Yes, like
Yes, 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 yes.
it's the same. Yes.
Yes, it is exactly the same. Thank you. Okay. That's another aspect of this. And this is why I bring this up. All right. And that is that, look, large numbers, we generally don't worry about all the actual exact precise value of that number. Give me enough digits that I'm happy, but tell me what value those digits take on. And that's what we've done here. We've gone just 6 digits in accuracy, or 5 digits total in accuracy, and then simply told you that I've got to move a decimal point, or I've got to move, yes, a decimal point back 13 spaces to the right to actually represent something close to that number. All right. So yes, you use the letter E, okay, for exponent, basically, that tells you this is 10 to the 13th power. So you've seen this in some form. And then the point Vladimir was making is right here. If I'm going to do this correctly, I should round this up to a 5 because the next digit is 5 or more. So that this would become 3.1455 times 10 to the 13th. Scientific notation, representing a number using a numeral or a method to represent what's most important. So that's something that, again, all we're doing is talking about counting, and yet big numbers, small numbers, the count has to be changed. You know, the way in which we represent the number has to be changed. The numeral that we use to represent it, all right, is probably going to be changed. So yes, you see that. Coronavirus, average size, 125 nanometers. What's a nanometer? Do we know?
It's like 10 in -7th exponent, like this.
Is it? Yes, you're exactly correct. It would be 10, but is it to the -7th or is it more?
9.
I
Negative
think
9.
it's I think it's 9, right? Because a nanometer would be one, would that be 1/1000th of a meter? Am I right? I think so. I think I'm correct. You know, and again, I mean, I could go back and do this too mathematically. The point is, no, when you start getting to negative exponents, it's a little harder for us, isn't it? To picture it, to represent it, to so forth. We could figure that all out. It would be 1.25 times 10 to the probably -11th, it's my guess. All right, what that would turn out to be because of how I have to move the decimal. -9, no, maybe -10th, maybe 10 to the -10th. I have to figure that out. But in any case, the point is trying to indicate what that is in a way that is compact involves more than just place value. We get down to other features. And then we talked yesterday about counting using a combination or a permutation. Yesterday we talked about, I've got 3 people. Let's take my 3 people to be Darnia, Oksana, and Max, right? And I want to make up a committee of people. And it doesn't matter what order in which I select them. And we said I could have 3 committees, 3 different ones. Maybe Max and Oksana, maybe Oksana and Dora, maybe Dora and Max. That would be my committee. But if it mattered which one I picked first, maybe we made Dora the president, all right, and Oksana the vice president, and Max the treasurer, all right? It would matter which one I picked first, which one I picked second, which one I picked third. And that's something called a permutation. What is this down here? What is this thing? What's that? What's that?
Factorial.
Yes, it's a factorial, right? And what's that mean? What do you do with a factorial? What operation is that?
We need multiplication numbers.
Multiply,
Um,
right? It's a multiplication. So what would n factorial be? What would 3 factorial be?
6.
It would be
6.
6. 3 times 2 times 1. So it would be 6, right? And then n minus x factorial. If x was 2, that would be 3 minus 2 is 1. What's 1 factorial?
1.
1.
Only one. Yes.
Yep. And since x is 2, what's 2 factorial?
2.
2.
2. So I've got 6 divided by 1 times 2, or 3 for combinations. This is an equation, an expression, and again, we've moved from arithmetic to algebra. This is an expression that determines how many combinations I might have. All right? If, on the other hand, I didn't have the x factorial for a permutation, then the 2 would be gone, and I would have simply 6 divided by 1, or 6 permutations, 6 different ways in which I could elect a president, a vice president, and a treasurer. 3 for the first case, 2 for the second case, 1 for the last case. 3 times 2 times 1 is 6. So all of a sudden we move into some algebra, some ways to express this answer when it comes to dealing with larger numbers in the process. All of this, every bit of this, is nothing more than counting. So yes, I can understand under unique circumstances, new circumstances, how you can miscount things. And yet that's simply basic elementary mathematics. And that's the kind of stuff where the mistakes show up. And that's the kind of stuff that you need to emphasize when you're teaching or working in higher level classes, being extremely careful about that part of your work. All right, enough said about that. I don't need to change that. I can get rid of my locks. Of course, we know there's much more to math than counting, don't we? Okay. I don't know if you use the same symbols there that we used here. The numbers we've worked with so far are natural numbers to begin with, 1, 2, 3, etc. Do you know what I mean when I say etc.?
Yes.
You're okay.
Yes.
Boom, boom, boom. Yep. Dot, 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 dot. 4, 5, 6, 7, etc. All right. And we throw in 0. All right. We call those the whole numbers now when we add 0 to that list. And now when we start talking about negative numbers, we refer to them as the integers. And then when we start talking about what are rational numbers? Dora, what's a rational number?
It's natural whole integers and
Give me one
of
example. Give me
fractions.
one example of a rational number.
P number P.
Number D.
P 3 dot 14.
Pi.
Pi.
Thank you.
Just
All right,
in Ukrainian we
Hold
say
on.
P.
No, now I understand your answer. Thank you. And again, this is English, right? So I understand your answer. We would refer to that as pi, right?
Pi.
We
Just in
refer to that as-
Ukrainian language we say P. Number P.
Yeah, understood. Again, just a cultural thing, right? Just a little difference there. But you're right. I'm right. I'm always right. But yeah, we call that pi. And as a consequence, that's not a rational number. Pi is not rational. Oksana, can you give me an example of a rational number?
Your microphone is off.
Sorry. 5 divided on 9.
Great. 5/9, a fraction, right?
Yes.
A rational number is any number that can be written as a fraction. All right. So our whole numbers are rational. I could write 2 as 2/1. If it can be written as a fraction and without changing its value, then it is rational. There are decimals like decimal 5, which would be 1/2, right? 0.5. That's rational because I can write it as a fraction. There are certain, well, what fraction would decimal point 33333333333 forever? What would that be as a fraction? Max, any idea? A decimal that never ends.
It's like number in braces.
Great. But can you give it to me as a fraction? Wonder if I can write that someplace.
1 divided on 3.
Yeah, done. Exactly. Correct. All right. If I were to do, and I'll just type it up here, I'll do a 0 and a decimal point, 3333333, and it just goes on forever, right? That would be equal to 1 divided by 3. 1/3. Does that make sense to everybody? That's a rational number. That's what we call a repeating decimal. And that repeating decimal can be written as a fraction. But then there are certain things like pi. All right. Pi, 3.141592653558, blah, 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 goes on forever and ever and ever. I've got a poster over here to my left that has maybe a few thousand digits representing pi. It doesn't end. It doesn't repeat. All right. It doesn't terminate. And it's called an irrational number. Non-terminating, non-repeating decimals. You all know what pi is worth, if I'm not mistaken. All right. Can you think of any other irrational numbers? Can anyone tell me a number that's irrational?
Number E.
E. What's E worth? Can you?
2.71 or 72.
Yeah, that's good. All right. 2.71828, a little bit of repetition, but then the repetition ends there. All right. So 2.71828. Yeah. All right. So yeah, there's another irrational number. Can anyone think of another irrational number?
Number P. P.
Well, there we go. There's another. I don't know that that's a different speaking, but phi, fi fo fum. All right. Phi is a. Can you tell me what phi is worth? Roughly. What decimal? No idea.
Your
Anybody?
microphone is off again. Your mic is off.
3.14159.
Okay, here we go. That's you guys call it p.
P.
I call
Yes.
it pi. That's an irrational number. But there's another irrational number called phi or phi. It's another Greek letter. I don't know what it would be in your situation. There's another one called the golden. I don't know what the next word is, but yeah, it's it's a ratio. No, it's not even a ratio. The point is, there's another very famous one. It happens to be 1.618. Does that number ring any bells? It's not as famous as pi. It's not as famous as or as phi as you p. It's not as famous as p as you call it. It's not as
It's
famous
called
as e.
it's called golden ratio. Golden
Yes,
ratio.
thank you. All right. I hesitated to use the word ratio because that suggests a fraction. And in fact, it suggests a rational number, and it is not rational. You can use a fraction to represent it, but that involves a square root. All right. Can anyone tell me what the square root of 2 is closely, roughly? What's the square root of 2?
Four. Yes.
What?
4.
Watch it. That's 2 squared. Again, maybe this is English, but that's 2 times 2. I want to know
1.42.
I want to know this.
1.42.
Okay, 1.42. All right. If you take 1.42 roughly times 1.42, you will get 2. Okay. But again, that's an approximation. Many, many square roots are irrational. You can't write them as fractions, not accurately. Square root of 2 is an example. So look, there's this whole other batch of numbers that don't fit into our fractional form, that can't be represented exactly, that we have to approximate. And in doing so, we have to decide just how close to the actual number we want to go, how many digits of accuracy. So all of that being said, oh, there's also something called the complex numbers, right? Or the imaginary numbers. Can someone give me an idea as to what an imaginary number is? Can someone give me an example? No engineers, huh? Vladimir, do you know what an imaginary number is?
Times I. I, it's like square root out of -1.
Yes,
So
square
just
root of -1,
imagine.
I, okay? Goes off into a realm that generally we don't have to deal with. Understand it's being or needs to be used when it comes to engineering theory in any case. So look, we started off really simple. 1, 2, 3, 4, 5, etc. We have digits. We may build numbers with those. We start doing other things other than just building up counting numbers. And so our system is far more complex than what we initially think about, what we initially see. This diagram kind of relates all of those and identifies some of the numbers that would fit into those categories. 1, 2, 3, 4, 5, 6, etc. Throw in 0, whole numbers, throw in negative numbers, we have integers, throw in fractions, anything that may be written as a fraction, and we have the rational numbers. Throw in those special things, pi, square root of 2, e, phi, all right? Those are irrational. They can't be represented as a fraction in any sort of accuracy. All right. Irrationals are a completely separate set of numbers than rationals. And then throw in these imaginary numbers, and we have what is called the complex number system. That's the number system that we work on. That's the number system that we are based on. Okay. You're based on it. I'm based on it. And if we can understand that entire system, it makes it easier for us to understand some of the arithmetic that we need to do. Any comments or questions on what we've done so far? It's a math thing so far. All right. We'll go a little bit more in terms of, and it's an arithmetic thing so far, but it just identifies how complex our number system can get and where there's room for mistakes that the kids make, that our students make when they're trying to do higher level mathematics. That's the one I want. Now it's a question of what do we do with numbers? We count. We measure, which adds another layer of difficulty. We try and arrange numbers in order, greater than, less than, equal to. We add, we subtract, we multiply, we divide. We use powers, we raise things to a power. We take square roots or cube roots or other kinds of roots, trying to find what numbers we multiply together to get an answer. And then we also work with something called absolute value. Can any of you tell me, can one of you tell me what absolute value is? What do I mean by absolute value? Max, no? Well, go ahead. Dora?
It's
Give me an example.
only positive number. Just yeah.
Yeah. Right? No negatives, right? Absolute value of
Yes.
absolute value of -5 is just 5. All right.
Yes.
In terms of a definition, a simple definition, it's the distance of a number on the number line from 0. How far away from 0 are we? No positives, no negatives. It's just the number. All right. So yeah, that comes into play frequently where the sign gets dropped if there is any sign at all. There's an order in which we perform operations. Here's an expression. I'm going to kind of highlight it. Can one of you tell me what that is equal to?
16. 16.
2. No? Yeah, it's 2.
No.
It should be 1.
It should be
It should be
1.
2. No, it should be 1, yeah.
It should
Sure.
be 1.
1.
Yeah, there's a priority. There's a order of operations here. The first thing that must be taken care of is what's in parentheses. 2 plus 2, right? 4. The second thing that must be taken care of is this multiplication right here. Now, this 2 doesn't show any multiplication sign. That's something that's actually called juxtaposition. When there is no sign like that, we presume it's multiplication. 2 times 4 is 8. And then the next thing that finally gets taken care of is this division sign. 8 divided by 8 is 1. So yes, I get 1 out of this. All right. And here's another example of juxtaposition where, again, I'm going away from just math or just arithmetic to algebra. So I have 2 times A times B divided by 2 times A.
B.
What's that equal to?
B.
Just B, right?
Yes.
Okay. And so, yeah, you have to decide what order in which things must occur, and you don't get to decide. It's predetermined. All right. You handle parentheses, then exponents, then multiply and divide. They're on the same level, then add and subtract. And tucked in there is something called juxtaposition. And prior to any of that, you have to kind of evaluate a number as either positive or negative. So there is a priority of operations. Suddenly our number system is becoming far more complex. And that's where kids start to kind of get lost. If they understand these principles, then they should be able to do any arithmetic work and any calculus work accurately if they understand differentials and they understand integrals. All right. but that's where they make their mistakes. And there's reason for that. It's that they don't understand the arithmetic. There are properties that our numbers have. Closure, identity, inverse, associative, commutative, distributive properties. All right? Telling you how parentheses might work or how the order of the numbers might work. All right? If they understand those properties, they should be able to handle the arithmetic that we're trying to do. I almost, unless it's a very simple problem, I almost never do subtraction. I always change it to addition of the opposite, addition in this case of a negative. Unless it's a very simple problem, I rarely do division. I usually end up changing it to multiplication by the reciprocal. All right? Flipping the number over and multiplying. It just simplifies your life. In fact, you notice all these rules are written only for addition or multiplication, because there's never any need to rewrite rules for division, or for subtraction or division, because I just change them, make them addition, make them multiplication. And that, again, should simplify your work. If your kids understand this when they're in a calculus course or a higher level course, an algebra course, then they're less prone to making mistakes. The problem is we don't go deep enough, at least in this country, to get the kids, to get the students to understand this mathematics, this arithmetic behind the work that they do. So here's a little arithmetic for you. Can someone answer that question?
$21.
42. Oh, yeah, 42.
All right, let's find out. What do we think a horse is worth?
I
10.
think it's 16.
So a horse is worth 10. So we're good with that. Okay. So what do we think a horseshoe is worth?
4.
So if I had 10 plus 8, because if a horseshoe is worth 4, then 2 horseshoes would be 8. So is 10 plus 8 plus 8, 18?
4.
4. I
Just
said
it.
4. Yes.
Just 4.
Okay. Is 1 horseshoe worth 4?
Yes.
Oh, it's 2. It's 2.
Pia.
1 horseshoe has got to be worth 2, because if I go to the second equation, I have a horse, which is 10, plus 2 horseshoes, so 2 plus 2 is 4, plus 2 more horseshoes, which is 2 plus 2, which is 4. So 10 plus 4 is 18. So a horse is worth 10, a horseshoe is worth 2. What's a boot worth?
One.
Got to be worth 1. I've got 2 horseshoes, that's 4. I've got 2 boots that I'm subtracting, and I'm getting a 2 as an answer. So 4 minus what is 2? 4 minus 2 is 2. But there are 2 boots, so each boot must be worth 1. So
It's
I have
21.
So I've got 1 for the boot, 10 for the horse, and 2 for the horseshoe. What's the answer?
13.
Oh, I'm sorry. I heard the answer. What was it?
13.
21. It's
21.
21.
Ah, so
I've got a multiplication problem taking place. 10 times 2 is 20. That takes place first, priority of operations. And then I add 1 and I get 21, right? All simple arithmetic. But now we understand why the students can make easy mistakes, because it's a lot of material there that we don't do, at least in this country, that we don't do. I won't say we don't do a very good job. I will say we do a poor job of teaching those concepts, all right, in our elementary schools, that make it more difficult for kids to take higher level math and science courses. And that's the concern as far as I'm concerned. I know it's a little bit early, but you're going to take a 10-minute break until, what would that be, 5 o'clock? So take a 11-minute break, 10-minute break until 5 o'clock, and then we'll move on. We okay? I'll be back.